The next question of CodeShip Starters 117 is Stingy arrays.
So the question Stingy array says is basically about a game where two players are playing as usual, Alice and Bob. Seems like they keep playing games itself. Okay. In this question says we'll be given an array. Array, let's say A of size n. Okay. Yeah. Players will play in turn. First, Alice will play, then Bob will play. Yeah. At each turn, what Alice will do or Bob will do is he'll select a subsequence from array A such that the subsequence is stingy. Stingy in the sense if we assume any subsequence or a set of elements, according to the question, stingy means 1, 2, 3. This is a stingy subsequence of sub array, we can say. Stingy means adjacent should be different. Like they should not be same. Even this is a stingy array. Adjacents are different. And this is not a stingy array. Yeah. So basically, they can only select a stingy subsequence. This is what the question is asking.
And that should be the longest among all.
Yeah, that should be the longest. Yeah. If we consider a sample test case, which is 1, 1, 2, and 3. First, Alice will play down. He has to select a stingy subsequence, which is largest as possible. Yeah. Can we say 1, 2, 3 is a stingy subsequence? Yeah. Yes, it is because adjacents are not duplicate. So he will, on his turn, he'll select these and remove it from the array. Yeah. Only array after Bob's play, only array will be remaining is 1. Yeah. Correct. Now when Bob's turns come, he will remove the only leftover element and will be left with nothing. Bob has played his turn. Now when Alice play turns come, Alice will not be able to pick any element. That means all the elements are already picked or removed. So Alice loses the game. Who will win is Bob will win. So for the first sample test case for array 1, 2, 3, we'll print Bob as output because Bob won the game. So this is the question. We'll look at another sample test case for better understanding. If we have 2, 2, 2, 2 as array, no matter what sub-arrow subsequence you pick, we cannot pick more than one element as all the elements are same. So Alice Bob for two players. First term will go to Alice. At his term, he'll remove 1, 2. Array will be remaining is 2, 2. At Bob's turn, he'll remove 1, 2 again. Array will be remaining is 2, 2. At Alice's turn, he'll remove 2 again. And only element will be remaining is 2. At Bob's turn, he'll remove the whatever leftover it is. Yes. And nothing will be left. That means the last turn which was played was by Bob, and Alice could not play anymore. Again, Bob is the winner. Yeah. Yes. So we will move forward with the last test case, which might be confusing, or another similar test case 1, 2, 3, 2, 2, 2. If this was a test case, can we say largest subsequence that Alice can pick is 1, 2, 3, and 2? Yeah. Is it correct? So this is a stingy subsequence that Alice will remove, and only left element are 2, 2. Alice will remove this. For Bob, only 2, 2 will be removed. He'll remove only 1, 2. Yeah. Only 2 will be remain for Alice, and he'll remove the last. Yeah. And Bob will be left with nothing. That means he cannot play his turn. Alice won in this case. Yeah. So this is the question. Question is straightforward. Let's move to the approach. Let's see who can win and how we can win. Yeah. Yeah, about the input format and constraints. Like any other input format will be given T, that is number of test cases, N, and A. Yeah. A is the input array here, N is the size of the input array. Yeah. And according to the constraints, size of the array can be inside the range 1 and 10 power 3 into 10 power 5. Yeah. And every array element will be in the range 1 to N. Yeah. Yeah. So this is the constraints.
So let's see how we can solve this problem. So basically, we know that Alice in each player's turn, they'll pick the longest subsequence, which is longest subsequence, which is stingy, right? So stingy definition is already defined. So now let's see. So as a just stingy is a subsequence where adjacent elements are different, right? So now, firstly, let's see how we can do a brute force to find our answer, and let's see how we can optimize the same route. So, in the brute force, what we can do is we can do it in a greedy way to pick the elements. So initially, it's Alice turn, right? So in Alice turn, let's see what all elements could she remove. She could remove this, then this, then this, then this, then this, then this. So all these elements she could remove. So the leftover elements after Alice removing the elements would be 1, comma 1, comma 2, comma 1, 2, comma 4, comma 6, comma 6. These are the elements after Alice removing the elements in her turn R, right? Now it's Bob's move. In the case of Bob, he'll remove this, then he'll remove this, 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 right? Then we'll get 1, comma 1, comma 1, comma 1, comma 2, comma 6, right? Now these are the leftover elements. Now let's see how many could Alice remove. Now in Alice's turn, she can remove this. So basically, I'm writing in Alice turn after removing what is the sequence, and from that sequence, what all Bob could remove. Now, after Bob removing, this was the sequence, right? From this sequence, which all can Alice remove? Alice could remove this, and this, right? Then 1, comma 1, comma 1 are the leftover things. Right? Now, it's Bob's turn. Bob could remove only a single one, which is the longest stingy sequence. And now Alice could remove only one, and one is left. And now it's Bob's turn. Now Bob could remove one, right, which is left. So now the array became empty, right? And now it's Alice's turn. So Alice can't perform anymore, right? So we can say Bob is the winner of the game. But now here, to find the stingy sequence for every turn, what we could greedily do is in the brute force we can run a loop from left to right, and we can maintain the previous element that is picked. Initially, we can make it any invalid element. So initially we are picking one. Then next, this is the one present, right? That is equal to the previous element that is picked. So we ignore it. Then this one also we ignore. Then two is different from the previous element. We include two. Then this two we ignore. Next one is different, so we include. Three is different, we include. One is different, we include, and so on, right? So we'll run a loop from one to all the elements present, right? And then we remove the stingy sequence that is picked till now. So if we look at the time complexity for this might look like it is faster, but it's not actually faster. It might look like because we are removing the elements, it's faster. But there is a worst case where if we have lengthy lengthy block, if we have lengthy block with same characters, so if we have lengthy block with same characters, then we can observe that from here we are iterating a loop, checking for each and every character,
And we are removing
and we are removing only one. Similarly, from here we iterate a loop, we remove only this. From here we iterate, remove only this, and so on. So we can see this is turning out to be n square. Right? Now let's see if we can make the same thing faster. So this turned out to be n square. but these observations are sufficient enough to make it faster. Right? So let's greedily pick the sequence, stingy sequence. So same greedy observation we can do over here. So we can process them greedily only, but the way we are processing, we can change it a bit. So let's write out the same sequence. Three, comma, 1, 3, 2, 2, 4, 1, 5, 3, 6. And then we have 3, 6. So this is the initial sequence. N is equal to 21. So now what we can do is we can do something like a BFS. In the first level, initially, what all elements do we have? Compressed elements. So let's see how we'll compress those elements. And in the next level, what all compressed elements we have. In the next level, what all compressed elements we have, and so on until it becomes empty. So let's see how do we process them. So here, initially, let's compress the elements as follows. 1 represents the element and the length of the block, like how many consecutive ones we have, starting from the first one. So we have 3. So this is one block. 2 till 2 and the frequency of that block. So it is 2 comma 2. Right? Then from this one, the frequency of the block 1 comma 4. Then it is 3 comma 1, 1 comma 2. Then it is 1 comma 2 comma 3, 2 comma 3, 4 comma 2, and 4 comma 2. 5 comma 1 and 6 comma 3. 5 comma 1 and last one is 6 comma 3. Right? So now let us write out these things for each level. So if we process the same thing greedily, previously what happened was we were picking the elements which we don't remove. We were iterating over elements which we don't remove also. Right? But now let's only iterate on those elements which we remove. So that means for every iteration we are removing one element. So can we say we only perform n iterations? So let's see. Initially this is at 0th level. Right? So at the first level, we should pick one stingy sequence, longest stingy subsequence. So that is just longest stingy subsequence is nothing but removing one from each of this, right? Because we know one fact of this compressed sequence, that is every adjacent element is different because we already compress them as per their block frequency. So we can remove 1 from this 3. Let's remove a 1. From 2, let's remove a 1. Right? From this one, let's remove a 1, which becomes 3. From this 3, we'll remove a 1. Then this becomes 0, right? If this becomes 0, then we don't include this. So we can maintain a new list where we append all those which belong to the next level, right? There we won't append this. So that way we can implement. And here 1 becomes 1. This I'll just mark the block which is removed. This is removed. And for every block we are reducing its frequency by 1 because every element we pick once. Right? And for the next one it is 2 comma 2. Then it is 4 comma 1. Right? Then it is 5 comma 0, but we don't add this. So we remove this. And 6 comma 2. Right? After the first level, this is how the frequencies got changed. Now let's see at the second level what happens. In the second level, 1 comma 2 is present. Right? This is the block. And okay, here we need to remove also. So let's remove one element. So it becomes 1 comma 1. So that means by level we can just say which player is playing. Right? Zeroth level, like it was Alice turn. When like in level 1 Alice played actually. Right? When it was level 1 Alice played, level 2 now Bob is playing. So 2 comma 0, right? So we ignore this. We'll remove this. Right? Now Now, from this block, we remove one element, that is 1 comma 2. Right? But if we see, our aim was not to iterate on duplicates, right? That means we compress these sequences and maintain them in such a way that every adjacent block elements are different. Because every adjacent block element should be different, here if we add the blocks as follows 1 comma 1 and 1 comma 2, they'll be same, right? So what we do if two blocks, if two blocks are same and they are adjacent, two blocks have same elements and they are adjacent, then we can merge those, right? So that's why what we do, I'll mark this as green, stating that this got merged with the left block. So we just merged it, and now the value becomes 1 comma 3, right? Why? Because we removed one from this, we removed one from this also. In the stingy sequence, we picked this and we picked this also. So that's why now in total we have 1 comma 1 and 1 comma 2 block, and we merged them. That became 1 comma 3. So we merged it. So we merged it to this. Right? This is how we can see. And now again, if we see, we have a 1 comma 1 block also, right? So this 1 comma 1 block is also getting merged. So there is a small issue in the previous level. So let's quick fix it. So here we didn't merge these, right? So if you observe, after removing 3, we removed 3, but these two should get merged, right? This one should get merged with this because we removed it. So we can quick fix this. So now we'll have 1 comma 4, right? So we merged uh, from 1 comma 4 we removed 1, and from 1 comma 2 we removed 1. That means we had 1 comma 3 and 1 comma 1. So I'll show how merge happened. 1 comma 3 was there, and to the side of it we had 1 comma 1, right? So these two are same elements, so we merged into the same. We merged them into one unit. So it is nothing but 1 comma 4. Right? And then we get 2 comma 2, 4 comma 1, and 6 comma 2. Right? These are the elements. Now let's see the second level. Now Bob is playing the game. So now the stingy sequence, after picking the stingy sequence, we remove 1 comma 1, and then it is 2 comma 0, right? This is 2 comma 0. That means we should remove this because it became 0 now. We don't consider this anymore. And 1 comma 3, right? So that means we can just observe that this got merged now. Right? These two got merged. So previously we merged this part with this. Now we are merging this part with this, right? Because we removed 2 comma 1. So that is why when we merge it, it becomes 1 comma 4, right? Comma 2 comma 1 comma 4 comma 0. So here 4 comma 0 we ignore this. Right? This is ignored. Why? Because the frequency becomes 0. And now 6 comma 1. Right? So now in level 3, 1 comma 3. Now level 3 in the sense it's Alice term. So it is 1 comma 3, 2 comma 0. Because it's 2 comma 0, we remove this also. and 6 comma 0, right? So this is also no more required because it's 0. So this is also removed in the next line. And now it is fourth level where Bob will play 1 comma 2. Now Alice will play 1 comma 1. Now it's Bob's turn. So it became 1 comma 0, right? So when it is Bob's turn, this became empty, right? Now 7, it's Alice's turn and he can't play a move. So we can say Bob is the winner. Bob is the winner. So it is just like in the first level, Alice played, then Bob played, Alice played, Bob played, Alice played, Bob played, and the last move played was by Bob, right? Alice couldn't play it. No. So Bob wins. Now here to analyze while analyzing the time complexity, we can see that we are visiting each and everything. We are whatever we are visiting, we are for sure removing that, right? So that means there are n elements. So we can see that we visit each and every element once only by maintaining these compressed with their frequencies. Right? For each visit, we are reducing the frequency by one. That is nothing but removing an element by removing the element from the original sequence. Right? So that is why we can say big of n is the time complexity of this, as we are just removing the as we are just removing the uh, as we are just subtracting the frequencies and whichever element we visit, for that for sure we are subtracting the frequency. That means just removing it from the original sequence. So space complexity of this is big of n, because we maintain a new list where we maintain all the compressed sequences, and that list length can at max be big of n. So we can say this times complexity is big of n and space is big of. These all are per test case. So, as a hint of implementation details, what you guys can do is you can compress each and every block and then store it in a list. Now, like you can run a loop. So basically, initially, let's say we have a queue and we have the initial compressed values. These are compressed. Right? So compressed values are just finding out the blocks with their frequencies, just like how we did here. Now we can run a loop until queue is not empty, until this won't be empty. Right? Uh, Now we can maintain all the next queue elements that will be present, and then we can iterate over elements in the queue, iterate over elements in the queue. So we can just be like for elements in all in the queue, and then just process the things that we are doing here. And then we can just and over here what we can do is put the next compressed elements in next queue, right? So now we can just say Q will become equal to next queue. So we are just doing BFS here. So here we can just maintain who is winning the game, right? So here 0 represents Bob is winning, 1 represents Alice is winning. So we can just perform XOR with 1 because XOR will just flip it to 0 and 1. So if who is 1, then Alice wins. Else Bob wins. So this way we can just implement it, just like similar to a kind of BFS, but not exactly BFS. and we see that each and every element we are visiting only once, and its time complexity is big of n. And space is big of n as we maintain a queue, and its space can be n in the worst case if all the elements are distinct. Right? So this is per test case, and if we look over uh, n depends on the test cases. So it's mentioned that summation of n over all test cases will be less than or equal to 3 into 10. So the worst scenario can be having one test case with 3 into 10 power 5 as n. So, so big of n time complexity is sufficient enough to pass in 1 second of t. This way we can solve it.